So in this lesson, we're looking at analyzing the theories of failure. So our main issue is just to investigate failure by applying some of the theories that have been applied as we look at how a component may fail. And then we'll come up with some assumptions to help us do this, and also some analytical formulas. Now here, like we're saying, we're going to come up with some design criteria or some formula. The idea is to ensure that we can explain the cause of failure, what could have caused this material to fail. Yeah, and of course, here we are going to, in this analysis, our focus is on gradual or static loads. We assume that we don't have those shock loads and others like impact loads, or name it, those in that category. Our very first stopover is the maximum principal stress theory. So in this analysis, according to this theory, failure will occur only when the principal stress, which can be stress 1 in the complex stress system, it reaches the value of the maximum elastic limit stress, meaning the stress at elastic limit in simple tension. We do the same even for a material loaded in compression, it's the same, but in this case, we talk about the stress reaching the elastic limit stress in simple compression. That's the only part. We respect the mode of application of the force or the nature of the stress. Can be compressive or tensile. So here we're saying that stress 1, which is the principal stress for the material loaded in tension, is equal to the elastic limit stress. Stress 3 is equal to stress EC. Let me just here emphasize. This is supposed to be stress EC. In fact, I can do this. Let me even just make it straight to the point. Yes. All right, so here we're saying that stress 1, sorry, get back there. This stress 3 is referring to the stress for the negative one for a material loaded in compression. We already mentioned that when you're loading a material in tension, the dimensions of such a material are going to increase. As a result, such a stress ends up being positive. That's for it, because even the force that is involved, the load that causes that is a tensile load. Here, it's a compressive load, hence a compressive stress. And that's why it comes out as negative. But when we're trying to compare it here, where we're saying that the stress reaching the elastic limit stress for a material loaded in compression, we ignore that negative and pick the absolute value. But we've already specified that this material is loaded in compression. So here is our case. We're saying at such a point, stress 1 can be either less than or equal to that general principal stress. Then comes the maximum shear stress theory. According to the maximum shear stress theory, we're saying that when this maximum shear stress it reaches the value of the maximum shear stress in simple compression or for elastic materials, then we expect that a material is going to fail. Practically writing it in a formula, we're saying stress 1 minus stress 3 over 2 equals stress ET over 2. These are representing the maximum shear stress. So let's pick up the last two parts. We equate the second and the third. What you find is that these two will cancel. And this is what you end up with, stress 1 minus stress 3 is equal to stress ET. So if there is 1 and 3, what about 2? We're saying that stress number 1 is for a material loaded in tension. So that's for a material. It's actually a tensile stress, a principal tensile stress. Then if you talk about stress 3, this is the one that comes out as negative. It will always come out as negative because it is a compressive principal stress. This principal stress is compressive. Now, if this is the case, then we have one missing link between these. You cannot just count 1, 3. What about 2? So you will find that in our analysis, we'll be including this same stress 2. But we'll be saying that stress number 2 is actually between the negative and the positive. So it's actually 0, most of the analysis. If it's not that, then there will be guys to take us there, to help us get to that. So when we're dealing with ductile materials, we have that. Stress 1 minus stress 3 being equal to the tensile stress. Here is the elastic limit stress that we are finding. Then, of course, whenever we are dealing with this, for us to find out what is stress 1, what is stress 3, we have to take our principal stresses through this calculation. And of interest, you notice that the bending stress that we are having here, to find it, sometimes it could just be given directly from the question, or you go back to the bending equation and calculate it. Information will be provided to guide you so that you can find that bending stress. Then you can come and substitute here and there. The same thing with the shear stress. You go back to the torsion equation, calculate for shear stress, and then come back and replace there. So in this case, we are saying principal stress is equal to bending stress over 2, then plus or minus under the root, bending stress over 2, everything in there, squared plus shear stress squared. Let me emphasize this side, everything is actually in the brackets, so it's supposed to be there, caged. What are the problems with this theory? Number 1, we don't expect accurate results as long as the maximum shear is developed. The results that are gotten from here are not going to be maximum. They're not accurate. And the other problem is that it's only applicable when the the stress that we're dealing with, you are not going to use this for a case where the stress consists of triaxial tensile stresses, where they are nearly equal to the magnitude, reducing the shear stress to a small magnitude. So here, the failure may end up being determined by other means. So we're saying for such a case, this may not be used. If you are carrying out experiments on ductile materials, you will notice that such may not give you accurate results. They will not take you numbers close to what you find in experimental results. All you will end up with are safe results. So this is yet another limitation. Let's look at some examples then. We have 2 examples that we're going to apply. In our first example, we have a metallic component. We taught this metallic component has a principal stresses of 35 meganewtons per square meter, negative 95 meganewtons per square meter. The third principal stress is 0, actually. Then the elastic limit in simple tension as well as in simple compression is 220 meganewtons per square meter. The criterion of failure for the material in the maximum principal stress theory. Oh, sorry. Let me just put this. If we are looking at The criterion of failure being the maximum principal stress theory calculates the factor of safety based on the elastic limit. Now, here we already have the elastic limit stress as well as these principal stresses. Before I proceed, we mentioned that the positive one is stress 1, the negative one is stress 3. Leaving out the other one in the middle, we emphasized that such a stress ends up being 0, as it has been clearly stated here. In some cases, we could be given guides, as we will see in the second example. Then we'll calculate 1 and 3, but number 2 is missing because of this simple reason that in most of these, majority of the cases, we take it as 0. Or in fact, for making our analysis smarter and simpler. Let's look at the information provided in our data. Stress number 1 is positive 35 meganewtons per square meter. We said number 1 is positive. Stress number 2 is between 3 and 1 because number 3 is negative 95 meganewtons per square meter. Now here, I'm going to emphasize that in our analysis as we start the working, we're going to say, we pick this, and then we just say 95, because in that case, it means we could have already taken the absolute values, and then we start our working. So that will give us our stress 3 like that to make our work much simpler. Let's go to the solution. In our factor of safety, we are going to use the 2 principal stresses, remembering very well that what we were given was that the elastic limit stress for simple tension as well as for a material in compression is the same number, 220 meganewtons per square meter. If you have enough time, you may decide to split them, where we say stress EC is 220, then you also go ahead and say stress ET, meaning the elastic limit stress for material loaded in tension is also equal to the same number, 220 megapascals. So here, factor of safety, we pick the elastic limit stress divided by this principal stress. So we have 220 divided by 35. What do we have? We have 6.286. And remember, we're looking for the factor of safety. In this factor of safety, we are actually investigating failure. We're investigating the likelihood of failure. So the factor of safety that we're supposed to pick is one that is supposed to tell us when a material is likely to fail. That factor of safety related to that is the one we're going to select. So then let's proceed to the next step and test the next one as well. So here is our factor of safety. This time we pick the compressive stress, and here again I will emphasize, we said, let's pick the positive value. So stress EC over the third principal stress, and it gives us 220 over 95. We've ignored the negative because we picked the absolute value. When you do that, you get 2.32. Now, considering that we are having 220 meganewtons per square meter as our principal stress, you can already notice that between this stress and the other stress, failure of this material is likely to occur because of this one. As a result, the factor of safety that we have at the moment is this one. Not this. This may mislead us. Failure is likely to occur because of this. Hence, our factor of safety that we're picking is this one for our investigation. And that is the conclusion we're making there, that actually the failure is likely to occur under the compressive principal stress. Therefore, the factor of safety is 2.32, or basically just 2.3. It's the same thing. So this is how you handle the first analysis, where we are applying the maximum principal stress theory. But in our discussion, we picked two. The first one was the maximum principal stress. Then we also had the maximum shear stress theory. Let's look at an example that will apply the latter. In this equation, rather in this question, what we've been given is mount steel shaft 120 millimeters diameter, subjected to a maximum torque of 20 kilonewton meters, and a maximum bending moment of 12 kilonewton meters at a particular section. Then we're told that the maximum elastic limit stress in simple tension is 220 meganewtons per square meter. Calculate the factor of safety if the analysis is based on the maximum shear stress theory. Well, with this information, let's start figuring out what we have at hand. And here, when you're trying to use the maximum shear stress theory, this is the one we said that the maximum shear stress, this one, is equal to, or basically, in fact, we even ignored this. We just said it's equal to stress 1 minus stress 3 being equal to that stress ET. So stress, let's take limit stress for that. And then it had that companion where we said we need to get because where do you even get this one? If you look at the question, we don't even have any stress anywhere. All we have is just, it's the maximum elastic limit stress, but we don't have the principal stresses 1 and 3, they are not there. So in that case, means we have to move back a bit. So let's start first of all, picking out the information that we have. Number 1, the diameter is actually 120 millimeters. If I divide this by 1,000, it becomes 0.12. Next, I have a torque of 20 kilonewton meters. We've always said that a kilo is 1,000, so I have 20,000 Newton meters. Then aside from that, I also have the moment, which is 12 kilonewton meters. So that's 12,000 Newton meters. Because again, we're just converting the kilo to that. We multiply this by 10 power 3. We multiply 12 by 1,000 or 10 power 3. Then this is our result, 12,000 Newton meters. Then we've been given the elastic limit stress for a material loaded in tension. That is 220 meganewtons per square meter. Now, looking back, you will notice, first of all, I need I, because in the equation that we need stress 1 and stress 3. We do not have those. To get them, we need to plant them in an equation that should have the bending stress as well as the shear stress. So if I start with figuring out the bending stress, I'll need to go to the bending equation, which is M over I is equal to stress over Y is equal to E over R. So I start with I, second moment of area about the neutral axis. So by D4 over 64, that's our formula. Our D is 0.12, so pi times 0.12 raised to power 4. Everything divided by 64, I get 1.018 times 10 power negative 5. Then I also have Y, which is D over 2, is equal to 0.12 over 2. 0.12 divided by 2, I get 0.06. So now I can apply this, the bending equation, the first two. Because in the bending equation, what we used to have was M over I is equal to, then I have the next one, which is the bending stress, over Y, which is equal to, once again, E over R. So I have this E, everything divided by R. Now this stress is the one we are calling the bending stress, because this is all about this is actually our bending equation. But looking at the information provided, this is of no use. We just need the first two sets to get what we're looking for. All these we have, there's a moment, we have calculated for I, we also have Y. So I can then proceed to substitute. In place of M, I have 12,000. In place of I have this number here, which is 1.018 multiplied by 10⁻⁵ is equal to, then there's a bending stress divided by, then I have the Y, which is 0.06. So if I make this the subject of the formula, it simply involves me cross multiplying there. And I'll have 70,735,530.263. The next thing I do, because I've already found the bending stress, I'm looking for now the shear stress. So I'll need to use the torsion equation. So I go back to J, modulus of rigidity, or rather the polar moment of inertia. I have pi d4 over 32. So pi times 0.12 raised to the power 4 divided by 32, which gives me 2.036 by 10⁻⁵. Then the next thing is T over J is equal to 2 shear stress over D. I need to make shear stress the subject, but I can do it smarter. T is 20,000, J is 2.036 by 10⁻⁵, D is 0.12. So transposing this whole thing for shear stress gives me 58,946,275.219. If you want, you can proceed to make this the subject of the formula before you do the substitution, or you do it this way, where you just proceed to the substitution, and then you calculate your final answer and you get where you're going. So what do I have now? I have the bending stress. I also have the shear stress, meaning I'm able to use that companion equation, this one, to find stress 1 and stress 3. So with this one, I have stress is equal to bending stress over 2 plus or minus stress B over 2 squared plus shear stress. So to find the first one, which is supposed to be stress 1, I'll just add here instead of subtracting. So when I do that, in fact, first I substitute. Bending stress was 70,735,530.263. Divide everything by 2. Then here we're saying plus or minus the same factor here, squared plus 58,946,275.218. So for the first one, which is stress 1, I'll ignore the negative. I'm going to add whatever I'm going to get under here to this result, meaning that I'll get a tensile force, which is stress 1, the positive one. And that answer is 104,110,344.2. That is stress 1, the principal tensile stress. The next one is stress 3, where this time around I subtract instead of adding. When I subtract this from the result coming from under the root, I get 33,374,813.9. Then we have the favorite, stress 2. Standing between the two, the positive and the negative, it's 0. With that, I can now go ahead and apply the maximum shear stress theory. Here, remember where we're coming from. We said that the maximum shear stress theory is given by stress 1 minus stress 3, which is equal to stress T. or stress ET. So with that, I have 104,1103.2 minus negative 33,374,813.9 is equal to that test of stress. So once I do that, my answer comes out as 137,485,158.1. 137,485,158.1 newtons per square meter. Factor of safety then. Since I now have this tensor of stress, I also have the elastic limit stress for material loaded in tension. I can now apply factor of safety, which is stress ET over that. So when I substitute, it's 220 by 10 power 6 divided by this answer I have here. And my answer for the factor of safety is 1.6. 1.6 is my factor of safety. So let me just roughly go through this. If you look at what we are looking at here, we were looking for the two stresses, stress 1 and stress 3, knowing very well that stress 2 is 0. And to do that, we needed first of all to fish out this and the bending stress because these were not provided. We calculate this by looking back, looking at the bending, using the bending equation, we were able to establish this. Using the torsion equation, we're able to establish this one. In the torsion equation, we can go for the full version. T over J is equal to, is equal to 2 shear stress over our D. And then from here, we proceeded to say, then in this case, what you have for shear stress, therefore, is basically just 2D, rather 2T over that JD. And of course, we know J is by D4 over 64. So if you want, this can easily also be reduced where by D4 over 32. So this being the case, you notice that if you want, this can now be simplified. I think this is one formula in machine design. It's very commonly used because this is 32, which is supposed to be on top. You end up with 16. So you have 16T. Oh, sorry, that's 16T over oh, sorry, not 16T, the other way around. The 16 is supposed to be below there. So here we're saying that this is by D4 over 32, by D4 over 32. So the 32 is on top, then the other one is below. So this will end up giving us, because that's the 32, you multiply it by 2, you have 64. So you have 64T over pi D cubed. And, or rather pi D raised to power, not 3, but because there's the D here, and that's 4, pi D raised to power 5. Again, for those of us that enjoy direct formulas, it will still take you to the same result. Now, all we are saying is that from the torsion equation, you're able to get your shear stress. And that's the one we plugged there. And we got 58. From the moment, the bending analysis of the bending moment equation, that equation is the one that helps us to get this value, to arrive at the bending stress. And with all that information, we're able to get stress 1, as well as stress 3. That is now simple. We can now go ahead and apply the maximum shear stress theory, where we said stress 1 minus stress 3 equals stress T. Suppose we had already been given stress T, the tensile stress for material loaded in tension, that more like acting the working principle stress. In that case, we were not going to trouble ourselves there. We were going to start our working from here. Something similar to what we started with. We just plumped the elastic limit stress and what we've been provided with, and we substitute and we get our final value. So with this, we already have our final answer, and this is our 1.6. So for now, these are the theories of failure we had to analyze today. And in the next one, we'll look at the other remaining ones and see how they can also help our analysis. Once again, you can reach out where you feel there's some clarity in the comment section, or you can still reach out to me.